understand the mechanical philosophy of the Panzer III, we must analyze its engineering logic, a logic defined by absolute precision and micro-tolerances. It begins where the machine meets the earth. The track link itself, the KGS-61, was a highly complex manganese steel casting. Measuring exactly 400 millimeters wide, it featured intricate, mathematically calculated pockets to drastically save weight while maintaining absolute structural rigidity. To connect these links, German engineers refused to let the steel pins float freely. At the micro level, each pin was machined with a highly precise retaining groove. A dedicated spring steel circlip locked perfectly into this groove. This eliminated the need for crude external hammer plates, ensuring absolute permanent alignment. This precision track rode beneath 6 paired road wheels per side. Each wheel utilized bolted steel construction, surrounded by thick, high-grade solid rubber tires to maximize vibration dampening. Inside the hub, rotational physics were governed by dual sets of precision-machined roller bearings, sealed tightly against dust to guarantee virtually frictionless operation. Each wheel was independently mounted to a forged steel swing arm. But the true genius of this suspension system was completely hidden entirely inside the armored hull. This is the torsion bar system. Instead of bulky external springs, a perfectly straight, highly tempered steel rod spans the entire internal width of the chassis floor. One end of the bar is attached to the moving swing arm, while the far end features intricately machined splines that lock immovably into a fixed anchor point on the opposite wall. When the road wheel encounters an obstacle, the swing arm is forced upward. This geometrically pivots the arm, turning vertical linear shock into pure rotational force. Because the far end is rigidly fixed, the entire steel rod physically twists along its axis. The immense shear stress of the twisting metal acts as a highly efficient, space-saving internal spring. However, torsion bars lack natural dampening. To prevent continuous bouncing, precision hydraulic shock absorbers forced fluid through calibrated microvalves, converting the kinetic energy into thermal heat. This sophisticated module was duplicated across 6 independent stations per side. It consumed internal floor space, but provided unparalleled cross-country stability. This resulted in an incredibly smooth, highly stable firing platform. The precision foundation was set. Now, it had to be armored. To armor the Panzer III, engineers utilized a geometric philosophy defined by stepped, nearly vertical armor plates. This boxy architecture was a deliberate choice to maximize internal space. With vertical surfaces, protection relied entirely on metallurgical quality. A standard 30mm plate served as the baseline for the hull's primary defense. The steel underwent a complex face-hardening process. In high-temperature ovens, carbon was infused exclusively into the outermost surface of the plate to create extreme surface tension. This created dual-property armor, a glass-hard outer face to break incoming shells, backed by a softer, flexible core designed to prevent internal fracturing. When hit, the face-hardened layer shatters the kinetic energy of the round. The softer inner steel then catches the remaining blow. Mathematically eliminating the risk of spalling. Assembly was an exercise in extreme precision. Edges were not simply cut, they were precision milled into complex interlocking rabbet and step joints. These plates slotted together with zero play. This mechanical interlocking allowed the hull to absorb heavy kinetic shear force without placing stress on the welds. Only then were the seams sealed. Highly skilled manual labor applied multiple precision passes, building a high-integrity bond that matched the quality of the parent plates. This precision geometry served the crew first. The vertical architecture maximized internal volume, creating a spacious and efficient combat environment. Survivability was integrated into the geometry. Large, double-door escape hatches were built into both sides of the hull, providing the crew with immediate, unobstructed exits. The layout followed strict compartmentalization. A solid armored firewall was bolted into position, isolating the operators from the noise, heat, and fire hazards of the engine. Design logic also prioritized maintenance. The front transmission armor was bolted, not welded, allowing the entire plate to be removed for rapid field diagnostics and repairs. To complete the hull structure, wide steel track guards were integrated, covering the complex suspension and providing standardized platforms for external stowage. The result was a precision-machined, face-hardened armored vault. A structure designed not just to survive, but to function as a high-performance command center. But to propel this sophisticated vault, an equally refined heart was required. In the isolated rear bay, the intricate architecture of the Maybach engine was ready for installation. To power this precision vault, German engineers relied on complex gasoline technology. The heart of the Panzer III was the Maybach HL120TRM, an 11.9-liter V12 engine. Unlike diesel engines that rely on pure compression, this gasoline power plant required exact air-fuel mixtures. Dual Solex carburetors geometrically blended atomized fuel and air before injecting it into the cylinders. Detonation was precisely controlled by high-voltage magnetos. These distributed electrical pulses across a complex wiring harness, arriving at the spark plugs in perfect microsecond timing. Inside the combustion chamber, the spark plug ignited the volatile gasoline vapor. This generated a highly controlled explosion, driving the pistons to produce 300 horsepower. To achieve maximum tactical mobility, the drive sprockets were located at the extreme front of the hull. This required routing the engine's power straight through the fighting compartment. A massive exposed steel drive shaft bisected the lower floor. This spinning cylinder carried immense torque directly beneath the crew, demanding a strict ergonomic solution. To protect the operators without losing space, an elevated sheet metal housing was bolted over the shaft. This geometric addition integrated seamlessly into the floor, acting as a safe stepping surface. This shaft delivered power directly to the front transmission block. This was the ZF SSG-77, a six-speed mechanical masterpiece that defined German automotive precision. Unlike primitive straight-cut gears that required brutal force, this gearbox featured advanced Synchromesh technology. Conical brass synchronizers perfectly matched the rotational velocity of the gears before they engaged. This eliminated mechanical binding. Shifting gears in a 20-ton Panzer III was virtually effortless, requiring only a gentle push. It was an absolute triumph of operational ergonomics. Power then split laterally into highly complex epicyclic steering units. By applying precision steering brakes, the driver could seamlessly cut power to one track, executing smooth, controlled turns. This torque finally reached the front drive sprockets, gripping the manganese track links and pulling the precision-armored vault forward. Even with this massive transmission block located inside the crew compartment, the vertical armor geometry preserved a spacious, fatigue-reducing environment for the driver and radio operator. The foundation was now fully mobile, an intricate, meticulously calculated, and utterly flawless mechanical system. With the spacious vertical hull, engineers were able to cut a massive 1,520mm turret ring. The stage was set for a revolutionary three-man turret. With the massive 1,520mm ring established, the highly complex, multifaceted turret was lowered into position. But the defining feature hung beneath it. A rigid, suspended, tubular cage formed a complete rotating floor, known as a turret basket. This structural floor physically isolated the upper operators from the static lower hull. It prevented them from stumbling over the drive shaft or ammunition bins during combat. The massive ring diameter permitted a revolutionary three-man layout. The internal volume was algorithmically divided into three dedicated, specialized operator zones. The rear zone belonged exclusively to the commander. Positioned centrally and elevated above the weapon system, the commander was completely freed from the physical labor of operating the gun. This elevated position capitalized on the tank's greatest tactical asset, the commander's cupola. A complex raised armored cylinder featuring 5 precision-machined viewports. Through high-grade armored glass, these 5 ports mathematically generated a perfect, overlapping, 360-degree field of view. Tactical blind spots were entirely eliminated. For protection, each thick glass block was shielded by external sliding armored shutters, allowing the commander to instantly seal the viewport against incoming shrapnel without opening the hatch. Forward of the commander, the labor was perfectly divided. The left zone was optimized exclusively for the gunner's targeting optics, while the right zone provided the loader unobstructed access to ammunition. For maximum survivability, the wide turret design incorporated large, double-door escape hatches on both flanks, ensuring the gunner and loader had immediate, dedicated exit paths. To aim, the gunner utilized an extremely precise, manually operated traverse gear system. While slower than an electric drive, it offered surgical accuracy for laying the gun on target. When traversing, the entire internal system, the seats, the floor, and the operators, rotated as a single, unified mathematical entity, allowing absolute focus on combat. Because of the elevated position, the commander possessed perfect internal geometric line of sight to oversee and direct the gunner and loader seamlessly. This three-man, ergonomically flawless turret was the ultimate command center. It was a masterpiece of cognitive optimization, ready to receive its primary weapon system. Everything was optimized. The torsion bars, the Synchromesh gearbox, the face-hardened armor, and the three-man turret. It was time to install the punch, the 5cm KWK-38. To complete the three-man turret, the primary armament was installed. The 5cm KWK-38 was inserted through the external armored mantlet. German engineering prioritized balance. The gun's trunnions were positioned exactly at its mathematical center of gravity, allowing the gunner to elevate or depress the weapon with virtually zero physical resistance. Linked directly to this balanced axis was the TZF-5 telescopic sight. A solid mechanical arm ensured the optics mirrored the gun's elevation with absolute mathematical precision. Inside the optic, high-grade Zeiss glass lenses refracted the light. Unplagued by bubbles or impurities, these lenses delivered a crystal-clear, undistorted field of view, guaranteeing lethal first-strike accuracy. On the loader side, ammunition was stowed in highly organized protective matrices. Geometric layout ensured an unobstructed, perfectly linear path from the storage bin directly to the breech. The 5cm Panzer III 39 was seated into the chamber. Crucially, the base of this casing lacked a percussion cap, utilizing an advanced electrical primer instead. Driven by a powerful torsion spring, the semi-automatic breech block snapped horizontally across the chamber. The massive steel wedge mathematically sealed the explosive force inside. Ignition was not achieved by a mechanical firing pin. Squeezing the trigger sent a high-voltage electrical pulse directly into the primer, initiating detonation with zero mechanical delay. The propellant detonated instantly. The precisely machined horizontal wedge contained the colossal pressure spike, directing all expanding gases exclusively forward. As the projectile was forced down the barrel, the internal rifling grabbed the driving band, imparting an immense gyroscopic spin to mathematically guarantee a flat, hyper-accurate trajectory. The resulting recoil generated immense rearward force. However, the perfectly balanced trunnions ensured the massive breech slid backwards with absolute, frictionless linearity. This kinetic energy was systematically absorbed by a highly advanced hydro-pneumatic system. Hydraulic fluid dissipated the violent shock, while compressed nitrogen gas stored the energy needed to return the gun to battery. As the pneumatic pressure gently returned the gun forward, the breech automatically slid open, cleanly ejecting the spent casing into a dedicated canvas catch bag beneath the gun. To preserve the pristine ergonomic environment, a mechanical deflector guard caught the toxic fumes. Powerful, highly calibrated ventilation vectors immediately sucked the exhaust gases safely out the roof. Optics perfectly slaved, a perfectly balanced gun axis, an automated breech, and a smoke-free environment. The Panzer III turret was the absolute pinnacle of functional combat ergonomics. The mechanical perfection of the Panzer III was amplified by its electronic integration. The front right hull was entirely dedicated to a specialized radio operator. Mounted within this zone was the FUG-5 transceiver. Every single Panzer III was equipped with this advanced communication system as a standard requirement. Internally, complex vacuum tube circuitry allowed for 10 watts of transmission power, guaranteeing a reliable voice communication range of up to 6 kilometers. Operating on the VHF band between 27 and 33 MHz, the system ensured crystal-clear, interference-free transmission across the battlefield. The signal was broadcast through a dedicated 2-meter copper rod antenna, flexibly mounted on the rear hull, to prevent snapping during turret rotation. This invisible electromagnetic sphere completely altered armored warfare. But to utilize it effectively, the entire crew had to be connected to the network. The Panzer III utilized an advanced internal intercom system. All 5 operators were integrated into a closed electrical loop, visualized here as 5 geometric nodes. Equipped with throat microphones and noise-canceling headsets, their communication was routed through a central junction box. Every member could hear and speak with perfect clarity. This eliminated reaction delay. The commander could instantly transmit targeting coordinates to the gunner and steering commands to the driver without taking his eyes off the optics. By completely eliminating the need for visual hand flags, which required opening hatches and looking away from targets, the speed of radio data transfer provided an insurmountable tactical advantage. When you scale this internal synergy across multiple units, the true power of the Panzer III emerges. 3 independent machines become a single, networked entity. Linked continuously by the FUG-5 radio, a platoon operated with hive mind coordination. They shared a unified, real-time picture of the battlefield. If one commander spotted a target, he could transmit the exact coordinates. Instantly, all 3 vehicles could mathematically converge their fire on a single point. This was the ultimate force multiplier. The math of warfare had changed. 3 heavily networked, ergonomically flawless units were vastly superior to 10 isolated machines. From the micro-tolerances of its bearings to the electromagnetic waves of its antenna, the Panzer III was a triumph of precision. It was a primary node in the ultimate combat network. In the German engineering doctrine, the precision machinery was secondary to the operators. The Panzer III was designed as a highly specialized life support system. To preserve operator efficiency, the internal volume was strictly compartmentalized. A solid armored firewall was bolted into place, completely isolating the crew from the engine bay. This wall geometrically trapped the extreme heat, acoustic violence, and fire hazards of the Maybach V12, maintaining a stable, fatigue-reducing environment inside the fighting compartment. However, a deadlier hazard existed inside the turret. Ejecting a spent 50mm casing released highly toxic propellant fumes directly into the sealed armored vault. To counter this, a mechanical deflector guard was integrated into the breech assembly. It instantly trapped the exhaust gases within a confined geometric zone. Simultaneously, a high-velocity extractor fan mounted on the roof engaged. Powerful aerodynamic vectors actively sucked the trapped fumes straight up and out into the atmosphere. This precise environmental control ensured the air remained sterile. By preventing carbon monoxide poisoning, the crew's cognitive endurance and reaction times were mathematically maximized. Even with perfect protection, a catastrophic hit was mathematically inevitable. Therefore, egress geometry was a foundational requirement, not an afterthought. The wide turret design easily accommodated large double-door escape hatches on both flanks. This ensured the gunner and loader possessed immediate, dedicated exit paths. For the driver and radio operator, dedicated lateral hatches were built directly into the lower hull. The geometry allowed them to drop out laterally, shielded by the tracks and road wheels. Because no crew member had to climb over another or wait for a single roof hatch, mathematical simulations proved the entire 5-man crew could evacuate the vehicle in under 5 seconds. To prevent catastrophic internal explosions, ammunition was stored exclusively in the lowest possible geometric zones, completely encased within heavy, armored storage bins. Even the engine bay was protected by automated safety logic. A built-in fire suppression system could chemically blanket the Maybach engine at the pull of a lever. If the hull was struck, the precision-milled rabbet joints proved their worth. The kinetic shock was routed entirely through the step geometry of the steel, completely bypassing the weld seams. From automated fire suppression to sterile ventilation and instant escape geometry, the Panzer III was more than a weapon. It was an uncompromising, mathematically optimized survival capsule. The extreme precision of the Panzer III came with a severe logistical penalty. Routine maintenance was a highly complex mathematical equation. If the advanced ZF gearbox failed, repairing it required extracting the entire massive transmission block directly out through the front of the vehicle. In field conditions, realigning the micro-tolerances of the Synchromesh cones was a mechanic's nightmare. Precision machinery demands precision maintenance. The sophisticated suspension posed similar challenges. Replacing a fractured torsion bar required pulling the entire steel rod laterally out of the hull, necessitating massive lateral clearance. Even removing a damaged road wheel required breaching the tightly sealed hub to extract the complex dual roller bearings without contaminating them with dirt. At the micro level, the precision spring steel circlips locking the track pins required specialized pliers to extract, a delicate geometric operation easily thwarted by battlefield mud. This relentless pursuit of mechanical perfection created an unavoidable equation. High precision equals excessive maintenance downtime. This bottleneck originated on the factory floor. The complex rabbet joints could not be rapidly stamped. They had to be slowly and meticulously milled from solid, high-hardness steel. The face-hardening process compounded the delay. Plates had to bake in specialized thermal ovens for extended periods to absorb carbon, paralyzing the speed of assembly. Even the final assembly relied on highly trained artisans. The multi-pass manual welding could not be automated, requiring specialized labor that was impossible to mass produce. When all these factors were aggregated, the mathematical output of the factories was severely bottlenecked. Producing a single Panzer III required over 4,000 man-hours. This complexity created a fragile supply chain. The vehicle demanded highly specific, non-standardized components from dozens of specialized factories. A single disruption halted production. This was the ultimate paradox of German armored philosophy. Uncompromising precision guaranteed tactical lethality, but unyielding complexity guaranteed strategic attrition. It was an immaculate machine, a masterpiece of metallurgical and ergonomic engineering, completely burdened by the weight of its own perfect tolerances. A vehicle that required an army of specialized artisans to build, and a university of mechanics to maintain. Beyond its armor and weaponry, the Panzer III's survival depended on tactical mobility. Moving a 20-ton steel vault across the battlefield required flawless dynamic kinematics. Steering a tracked vehicle is not achieved by turning a wheel, but by altering track speed. Power from the transmission was routed laterally into complex steering drums. Inside these drums lay the epicyclic or planetary gear system. A central sun gear mathematically drove multiple planet gears, transferring smooth, continuous rotational force. To initiate a turn, the driver engaged a steering lever. This actuated a heavy steel brake band that clamped down on the outer ring gear, applying massive frictional stopping power. This friction mathematically decoupled power to one side. The right track maintained full forward velocity, while the left track's momentum dropped immediately to zero. This differential caused the entire vehicle to pivot violently around the halted track. The chassis rotated with surgical precision along a perfect, mathematically predictable arc. Executing this maneuver imposed massive centrifugal shear force on the running gear. The lateral stress threatened to rip the track links directly off the road wheels. However, the tall, geometrically precise manganese guide horns of the track links locked flawlessly between the dual road wheels, completely neutralizing the lateral forces and preventing detracking. This intricate suspension also solved the physics of weight distribution. A mathematical ground pressure matrix reveals that the 6 road wheels distributed the 20 tons perfectly, preventing the vehicle from sinking into soft terrain. Mobility also meant conquering gravity. When approaching a 30-degree incline, the physical dynamics of the chassis were pushed to their limits. As the angle increases, the mathematical center of gravity shifts rearward. However, the elongated track footprint ensures the gravity vector remains safely within the base of support, preventing a rearward rollover. To overcome gravity, the driver selected first gear. The ZF transmission mathematically multiplied the Maybach's rotational force, converting high-speed RPM into massive, unyielding low-end torque. This torque was delivered to the track cleats, which bit deeply into the surface. Mathematical traction vectors confirmed absolute geometric grip, propelling the vault steadily upward. As the vehicle crested the incline and dropped flat, the brutal kinetic shock was instantly captured and mathematically dissipated by the torsion bars and hydraulic dampers. This absolute stability allowed the gunner to reacquire a target within milliseconds. The Panzer III's kinematics didn't just move the tank, they made the weapon system infinitely deadlier. Despite the crippling production hours and the logistical burden of its micro-tolerances, German industry still managed to mathematically replicate this precision vault by the thousands. This brings us to the ultimate mechanical logic chain. Individually, each subsystem of the Panzer III was a masterpiece of specialized, uncompromising engineering. The complex gasoline Maybach V12 mated flawlessly with a Synchromesh ZF transmission, delivering immense, frictionless torque without exhausting the driver. The face-hardened stepped hull was carried by the internal torsion bars, creating a perfectly stable firing platform that mathematically negated off-road vibrations. Into this stable vault descended the revolutionary three-man turret. The suspended basket isolated the crew, preserving absolute ergonomic superiority. With the chassis unified, the sensors came online. Crystal-clear Zeiss optics provided a 360-degree field of view, while the FUG-5 radio linked the machine to the battlefield. When merged into a single dynamic system, the Panzer III did not fight like a heavy tractor. It fought like a finely tuned instrument, capable of executing complex maneuvers while retaining perfect situational awareness. At the center of this mechanism were the 5 operators. Surrounded by face-hardened steel and connected by the internal intercom, their cognitive load was mathematically minimized. This minimized cognitive load transformed into tactical supremacy. Networked by radio, independent vehicles became a single, lethal, geometric hive mind. It was a design of uncompromising standards, a machine where precision mathematically equaled lethality, but unyielding complexity guaranteed strategic attrition. The Panzer III was not designed to be cheap, nor easy to build. It was designed to be the absolute pinnacle of functional combat ergonomics, a triumph of uncompromising mechanical logic, and a true testament to the obsessive nature of German armored precision. A flawless clockwork mechanism that forged the foundation of modern armored communications. This has been a mechanical deconstruction of the Panzer III. Subscribe for more deep dives into the raw engineering of military history.